Welcome to Section 3, a one-sample test for the mean. It's time to go back and look at the test for the mean that was introduced in 7.1, called the z-test. In that example, you knew the population standard deviation sigma. The question is, what if you do not know sigma? And more often than not, you're not going to know the population standard deviation. So we're going to go back through the questions from 7.1, but we're going to do them in a more realistic context. And that context is when we know the sample standard deviation in place of the population standard deviation. Now, we could use the sample standard deviation S as an approximation of the population standard deviation sigma. That means that the test statistic would now be exactly what it had been before, but instead of sigma divided by the square root of n in the denominator, it's now S, the sample standard deviation, divided by the square root of n. Notice that when we used z as our test statistic, the only thing that varied from one sample to another was x bar, the sample mean. Everything else was from the null hypothesis or the sample size. However, when we change the population standard deviation sigma to the sample standard deviation S, we now have two things that vary from sample to sample. X bar, of course, the sample mean, and S, the sample standard deviation. This gives us a different test statistic, no longer Z, now called T. T follows a different, not normal distribution that's still bell-shaped and symmetric. It's actually a family of distributions depending on the sample size. The t-distribution is also called a student's t-distribution. It requires that a random sample of size n is taken, and that either the distribution of the random variable is normal to begin with, or the sample size is over 30. Then the distribution of the test statistic, t, is a student's t-distribution with n minus 1 degrees of freedom. The degrees of freedom is another way that a student t-distribution takes into consideration the fact that there's two sources of variation in a t-distribution. So a degree of freedom can be thought of in the same way as people in chairs. If you have 5 people and 5 chairs, the first 4 people all have a choice of where they are going to sit, but the last person does not. There's only one seat left for that person. The last person has no freedom of where to sit, so only 4 people out of the 5 have freedom of choice. So our degree of freedom is n minus 1. The shape of the student t-distribution looks very similar to a standard normal curve. But as the degree of freedom changes, it varies from a standard normal curve. Let's take a look at how we compute probability with a Gossett student t-distribution. So let's go into our class resources and down to the applications for Chapter 6. We have the normal distribution calculator, and we also have the Gossett student t-distribution calculator. For example, if we know the mean, the standard deviation, and the degrees of freedom, we could find the probability of, let's say, being less than 43. And it'll tell us that 16.386, approximately, of the time we'd randomly select something in this distribution less than 43. A hypothesis test when the population standard deviation sigma is unknown has the following setup. First, you state the random variable and the parameter in words. X is the random variable and mu is the mean of the random variable. Then we state the null and alternative hypotheses and the level of significance. So just like before, the null hypothesis is the manufacturer's claim or the government data, mu equals mu null, where mu null is the hypothetical mean, the assumed mean, or the stated mean. There's still 3 choices for the alternative hypothesis, that the population mean is less than what's claimed, not equal to what's claimed, or more than what's claimed. And then we choose an appropriate level for alpha. Next, we state and check the assumptions of the hypothesis test. First, that we have a simple random sample, or better that it's representative, of sample size n. then that either the population of the random variable is already normally distributed, although the t-test is fairly robust when there is a large sample size. This means that if the condition is not met, that the initial random variable is normally distributed, but that your sample size is over 30, then the results of the t-test are valid. Now, this third assumption is simply ensuring that you're using the correct test. If you know the population standard deviation, then use a z-test as we did in 7.1. We're going to use t-tests only when the population standard deviation sigma is unknown. Then we find the sample statistic, test statistic, and p-value. The sample statistic is x bar, that is the sample mean, and S sub x, that is the sample standard deviation. Notice that I've changed the notation so that it matches our calculator. S sub x is what our calculator shows as the sample standard deviation, and that's just taking the place of a lowercase s. And of course our degrees of freedom are n-1. We'll use technology to calculate the p-value for you, and that will allow you to make a conclusion about the alternative hypothesis. And the same as before, at this point, you've seen this twice already. If the p-value is less than alpha, then reject the null hypothesis in favor of the alternative. Otherwise, fail to reject the null hypothesis and say that there is sufficient evidence to support the alternative hypothesis. Step 6 is when you state your interpretation in real-world terms of the initial problem. The conclusion for the hypothesis test is that you either have enough evidence to show that H sub A is true, or you do not have enough evidence to show that H sub A is true. So as an aside, note that if the assumptions behind this test are not valid, then obviously the conclusions you make from the test are also not valid. If you do not have a random sample, then it's your fault if you use the test. So make sure that the sample you take is as random as you can make it by following the sampling techniques from Chapter 1. If the population of the random variable is not normal, then take a sample larger than 30. If you can't afford to do that, or it's not logistically possible, then you do different tests that are called non-parametric tests. There's an entire course in statistics on non-parametric tests, and we're not going to discuss those in class. So get a sample size of at least 30, or make sure that it came from a normally distributed population to begin with. Okay, let's look at the first of two examples using a t-test for a hypothesis test of means. So from the website of IQ of Famous People, a random number generator was used to pick a sample of 20. So here is 20 randomly selected IQ scores of famous people. Does the data provide evidence at the 5% level of significance that the IQ of a famous person is higher than the average IQ of 100? So the first thing we're going to do is state the random variable and the parameter. Here the random variable is the IQ of a famous person. The parameter is the mean IQ of all famous people. Now the null and alternative hypotheses as well as the level of significance. The null hypothesis is there's nothing to see. The population mean among famous people is exactly the mean for everyone else. The null hypothesis is that mu is 100 for everyone. The alternative hypothesis is based on the question, does the data provide evidence that the IQ of a famous person is higher than the average IQ? So our alternative hypothesis is that the mean IQ of famous people is actually greater than 100. We're also told that alpha, our level of significance, is 5%. So alpha is 0.05. We now need to check the assumptions of this test. Well, we were told that a random number generator was used to select these 20 people. So clearly a simple random sample. We then remind ourselves that the IQ is known to be normally distributed. And then this last part is simply a reminder that we're doing the right test. We'd much prefer doing a z-test from 7.1 than a t-test in 7.3. There's only one source of variation when we're doing z-tests. There's two when we're doing t-tests. So we remind ourselves at no point were we given the population standard deviation, so we have to use a t-test. Okay, let's enter this data into a GeoGebra spreadsheet. So we're going into the applications for Chapter 7 and scrolling down to the IQ of famous people. So let's select that column and copy. Go into a GeoGebra spreadsheet. So we're going into View, turning on Spreadsheet, turning off Graphics and Algebra, and then let's paste that data in. Okay, with that data selected, let's do a one variable analysis and get the statistics. So it tells us that the mean is 145.4 and that the sample standard deviation is 29.2744. So let's put that information in. So there's our sample statistics, the sample mean 145.4 and the sample standard deviation. Now let's compute our test statistic, our t-score. So to do that we can use any calculator. Let's use the calculator built into our computer. So first let's compute the numerator, 145.4 minus 100. I'm going to press enter to force the calculator to compute the numerator. I'm then going to divide. I'm going to open parentheses in the denominator to make sure that that division happens down there. So the first thing is our sample standard deviation, 29.27. We're then going to divide that again by the square root of our sample size, 20. Let's close those parentheses, and it tells us that we're now leaving the denominator, and press enter. So there's our test statistic. And of course now we need our p-value, so let's look at the next page and continue with GeoGebra. So if I go back to the spreadsheet that gave us the statistics for the sample, I can click on that and go down to a t-test of a mean. Our null hypothesis is that the average is 100. We suspect that the true average is greater than 100. This gives us our p-value, and we can check that our t-score is the same. That's an excellent way of checking. Our p-value is 0. And so we can conclude that we reject the null hypothesis because our p-value is less than alpha. And we can say that there is enough evidence to support the claim that the average IQ of famous people is higher than the average IQ of all people. Okay, one more example, this time the lifespan of European males. In 2011, the average life expectancy for a woman in Europe was 79.8 years. The data in table 7.3.2 are the life expectancies for men in European countries in 2011 from the World Health Organization. Do the data indicate that men's life expectancy is less than women's? And we're testing this at the 1% level of significance. So a fair amount of data. It looks like all European countries are included in this. So let's get going. So the first thing we need to do is state the random variable and the parameter in words. The random variable x is the mean life expectancy of males in European countries. The parameter mu is the mean life expectancy of all European males. So the null hypothesis is that there is no difference. That is, the mean life expectancy of European males is the same as the life expectancy of European females, namely 79.8. Now the alternative hypothesis is that the life expectancy is less than the life expectancy for women. So when we create our alternative hypothesis, we're claiming that the life expectancy for men, mu, is less than that for women. We were told that the level of significance is 1%, so alpha is 0.01. The random requirement doesn't look like it is required here because it looks like we have every European country. There are some really small European countries that may not have been included in this, but n equals 53. So we don't have to worry about the sampling method because it looks like this was a census. So n is greater than 30, so the random variable can be assumed to be normally distributed. And that last requirement is simply that we're doing the correct test. The population standard deviation sigma is unknown. Okay, so now we need our sample statistics. So we are going to go into our applications for Chapter 7, scroll to the bottom for the lifespan of European men. Let's copy that and open a GeoGebra spreadsheet. So when we get in, we're going to go into View, turn on Spreadsheet, turn off Graphics and Algebra, and let's plug in that data. Okay, now we're going to select that column and do a one variable analysis and get our statistics. It looks like the mean is 73.7358 and the sample standard deviation is 5.7283. Okay, let's take that information back to the workbook. It looks like we have our sample statistics, and now let's find our t-score. So to calculate that, let's use the calculator built into our system. So let's do the numerator first, 73.7358 minus 79.8. Let's press enter to make sure the calculator computes the numerator. Let's then divide and open parentheses so that everything happens down there in the denominator. Our sample standard deviation, 5.7283. Just checking that that's correct, 5.7283. Then we're dividing that by the square root of 53. We then close the parentheses and press equals. And there's our test statistic, our t-value, negative 7.707 approximately. Okay, our next step is to use GeoGebra to find our p-value. So let's go from the statistics to the t-test of a mean. Let's put in 79.8 and then change this to less than 79.8 for the alternate hypothesis. We can see our t-value, so we're correct there. We have that information to confirm that GeoGebra is doing what we expected, and we have our p-value. So let's go in and state our p-value, approximately 0, which means that the p-value is less than alpha, our 1% level of significance. So we can say that there is enough evidence to support the claim that the mean life expectancy of European men is less than that for European women. And that concludes Chapter 7, our first look at hypothesis tests.